Hey guys, what's up? Hopefully you had a good couple of past days. We're going to try this instead of Zoom for now because of the processing delays on Zoom. I think YouTube handles processing probably in greater volume, so they shouldn't have any trouble processing stuff. So we'll see how this goes. Just use the chat feature to communicate, and I'll answer your questions as you have them. So I just want to kind of go over independence a little bit more today and do another Bayes Theorem example. We kind of made some good progress yesterday or Monday on what we were doing, so we don't really have a lot to do today, so I just want to go over these couple of things again and just recap and then do another example of Bayes Theorem. So kind of the main thing we talked about last time after Bayes Theorem was independence, and independence was this last thing right here. Like, that's the most important part for independence. So events are independent if the probability of A is unchanged given that the event B has already occurred. So the multiplication rule for independent events becomes probability of A times probability of B. So B has no effect on A has no effect on B. We talked about the generalized multiplication rule. So this is like a generalized multiplication rule right here. And that's really important. If you have mutually independent events, like so none of these events, A1, A2, AK, none of them are affecting each other, then you just multiply the individual probabilities together if you want to take the probability of the overall intersection of all of these events. So again, that was just kind of something that we wanted to cover last time. We looked at this example here. We worked it out. Let's do another example today. And this example is going to be another subsystem, but we just want to write it out. It's a little bit different. It's not the same as the last subsystem. So now this example says, assume that for the system to work, both these subsystems should work. So that means the top oval and the bottom oval both need to work. I think we're having some difficulties. I'm going to take 1 second, make sure that everybody can see everything. Take 1 second. Yeah, I have it pulled up on 2 different computers, making sure that I can see it. So I have it on a different computer where I'm looking at the chat and I can see everything. Maybe it'll just take a minute to load. If you started at the beginning, it would still be black possibly, but just hard to say. Yeah, so if not, you can always come back and watch the rest later. So if you have technical difficulties. Sweet. So we'll try to work through those before next time. Hopefully everybody can get on the same page quickly next time. Make sure there's no technical difficulties. So, all right, awesome. Let's go to this example. We basically need 1 or 2 and 3 and 4. So that's 1 or 2 and 3 and 4. So again, just remember that this is an or, this is an and, this is an and. So just a good, logical connection right there. The union is an or, intersection is an and. So how do we find the probability of this intersection? Well, these components should be independent of each other. So let's define a new event, call it B. So basically this thing right here, we're going to call that thing capital B. So now we want to find the probability of A1 or A2 and B. So we let B be this new event, A3 intersect A4. So this is going to be, the probability the system works is going to be the probability that A1 union A2 intersected with B. So that's really what we're trying to find the probability of. It should be 1 or 2 and 3 and 4, because in the example at the top here, it said assume that for the system to work, both the subsystems should work. So sure, if it were a circuit diagram and they were in parallel, you could have either one working. But here, the problem explicitly says both subsystems must work. So good question. Yeah, so that middle one is an and because of this both phrasing right here. So this both subsystems means that this should be an and, i.e. that should be an intersection right there. Good question. Normally, yeah, like a diagram like this, you would think, okay, this one could work or this one could work as long as I get whatever over to the other side. But it says both subsystems should work. So both ovals need to be functioning. All right, so let's look at how do we take the probability of this? Well, we could use the distributive laws, right? The distributive laws. Probability of A intersect B, A1 intersect B, union A2 intersect B. Yeah, if it didn't say both, then it would be the or operation. That's exactly right. If it said at least one subsystem must work, then it would be the or. Yeah, good questions. All right, so let's see. We got a union here. So how do we take the probability of a union? Well, we know that probability of, we'll call it C union D, is probability of C plus probability of D minus probability of C intersect D. So basically, this is going to be our C, and this is going to be our D when we take this probability of this union. So this is going to be, I'll write it over here, probability of A1 intersect B plus probability of A2 intersect B minus probability of A1 intersect B intersect A2 intersect B. But if I intersect B, I'm really just intersecting with B one time. You don't really have to write it twice like this, but I wrote it out twice just to be overly careful. That's our C intersect D, basically. So now, what we can do is we could say this is going to be probability of A1 intersected with B, but B is A3 intersected with A4 plus probability of A2 intersected with A3 intersected with A4 minus the probability of A1 intersected with A2 intersected with A3 intersected with A4. Because you could say that A1 intersect B intersect A2 intersect B is really just A1 intersect A2 intersect B. Because B is the same set in both. So you don't have to intersect it twice. You've already intersected with B. So that's what we can do here. Now, these are all independent events, and it said that the probability of AI is equal to, let's see, 0.9 for all I. And and the components are independent. So if the components are independent, then we can just multiply the individual probabilities together. So this is going to be probability of A1, so PA1 times PA2, or PA3, sorry, times PA4 plus probability A2 times probability A3 times probability A4 minus probability A1, probability A2, probability A3 times probability A4. So this is going to be 0.9 cubed plus 0.9 cubed minus 0.9 to the 4. And that turns out to be 0.8019. And that is the probability that this system will function. It's kind of low because we have to have both working. So a good thing for you to do, maybe to practice, would be, what if you only needed one of these to be functioning? What would the probability that the system works if you only needed one subsystem to work? So that's a good example. I enjoy that one. It's always makes you think. There's a harder one in the homework that you have to do. So just take your time working through these intersections and the unions and all this stuff. So just, again, post any questions over in the chat. I'll answer them as we go along. I'm not going to necessarily stop for questions each time. That dead space just gets kind of old, so we'll just keep going unless you just post something over in the chat. So let's look at, let's go back to Bayes' theorem a little bit. Let's review Bayes' theorem just from last time, that conditional probability stuff, where we talked about the law of total probability right here. So this law of total probability is like super important. So we do that. And then basically we use the multiplication principle to define Bayes' theorem, which said that the probability of AJ given B is probability of AJ intersect B over probability B. That's the definition of conditional probability. But then the multiplication principle in the numerator tells us I can write that as probability of B given AJ times probability AJ. But now the bottom, the denominator, is really just the law of total probability, rewriting probability of B. So that's Bayes' theorem. It basically takes you from like, what's the probability of AJ given B, to turning everything into probability of B given, you know, all the A's. So you can kind of like flip the question on its head and, you know, answer or multiply the other probabilities that you might already have. So let's look at a new example that's going to cover Bayes' theorem, or we're going to use Bayes' theorem in it. Part A is basically going to get the denominator for us, so we're not going to have to do the denominator in part B because we'll already have it. But this example says, the reviews editor for a certain scientific journal decides whether the review for any particular book should be short, 1 to 2 pages, medium, 3 to 4 pages, or long, which is 5 to 6 pages. Data on recent reviews indicates that 60% of them, 60% of the articles received are short, or sorry, reviews are short, 30% are medium, and 10% are long. So in a scientific journal, basically, like people submit their journal articles, but then they have to be peer reviewed. And those reviewers write up a little report. And they're saying, okay, the reports that we got back from the reviewers were 60% of the time they were 1 to 2 pages. 30% of the time they were 3 to 4 pages. And then 10% of the time they were 5 to 6 pages long. Now, it says reviews are submitted either in Word, so just like a Word document, or LaTeX. And LaTeX is a software, it's a typesetting software that we use in science to quickly generate, you know, these complicated symbols like integrals and, you know, even unions and intersections and all that kind of stuff. So you can use Word or LaTeX. There's like a plugin for LaTeX in Word, but most people use like the equation editor in Word, so it's like a little tedious. So it would be surprising if somebody used LaTeX for a longer document. Or sorry, if they used Word for a longer document. It's more likely that somebody's going to be using Word for a short document and a LaTeX for a longer document, especially a scientific document. So anyway, that's kind of the premise, the background, but you don't have to know all that to answer the question. But just to give you more context. So it says reviews are submitted in either Word or LaTeX. For short reviews, 80% are in Word, whereas 50% of medium reviews are in Word, and 30% of long reviews are written in Word. Suppose a recent review is randomly selected. Part A, what is the probability that the selected review was submitted in Word? So we got to figure out what are we already given. So we've got to pull from here what is already given. So what are we given? Well, we're given, I'm going to say L, or S is going to be the event of a short review. Medium, M, is going to be the event of a medium review. And L is going to be a long review. And then I'm going to say W is the event of review submitted in Word. And LaTeX is the event of a review submitted in LaTeX. So what are we given as far as like these percentages? What are these percentages? It says data on the recent reviews indicates that 60% of them are short. So probability of short is 0.6. Probability of medium is 0.3. So that's right here, 30% are medium. And then probability of long, see that's 10%, so 0.1. So we've got probability of short is 0.6, probability of medium is 0.3, probability of long is 0.1. Now reviews are submitted either in Word or LaTeX for short review. So given that it's a short review, 80% of those are in Word. So probability of Word given a short review is 0.8. So out of all the short reviews, 80% of them are in Word. So actually we could also get probability of LaTeX given short is 0.2 because that's the complement. If it's not Word, it's got to be LaTeX. Now, what's the probability of Word given medium? Probability of Word given medium is 0.5. So it's like the one right here, 0.5. And then probability of Word given long is 0.3. So probability of Word given long. Again, I can get the corresponding LaTeX probabilities. Probability of LaTeX given medium is 0.5, and probability of LaTeX given long is 0.7. So basically 70% of the time people would use LaTeX to write the long review. So that's how you kind of interpret these probabilities. So now part A, how do we get the probability, what is the probability that the selected document or the selected review was submitted in Word? So probability of Word, we're going to use the law of total probability to get the probability that a document or a review was submitted in Word. So that's going to be probability of Word given short times probability of short plus probability of Word given medium times probability of medium plus probability of Word given long times probability of long. So that's going to be 0.8 times 0.6 plus 0.5 times 0.3 plus 0.3 times 0.1. And that turns out to be, see, I calculated as 0.66, so 0.66. So basically 66% of the reviews are written in Word. How do you get probability of Word given medium equals 0.5? See, that says 50% of medium reviews are in Word. So 50%, this one is right there. Word given medium. It says 50% of medium. So given that it's a medium review, medium in length, it says 50% of those are in Word. So not sure if that clear that up. So that's the probability that a document is submitted in Word or a review is submitted in Word. So that means 44% of the time, not 40, sorry, 34% of the time, a document will be submitted in LaTeX, right? If it's not in Word, it's got to be in LaTeX. So 34% of the time, a document will be in, or a review will be submitted in LaTeX. Now, I know it doesn't ask for this, but it's just important to keep in mind, like, what all is there to work with? What all could we ask? What all could you try to find and things like that? So it's good to think about all this stuff while you're working a problem. Make sure you have it all straight. So part B, it says, if the selected review was submitted in Word format, what is the probability that first it was short? So part B, number 1, what's the probability of short given that it's a Word document? So what percentage of Word documents are short, basically? Like, given that it's a Word document, what percentage of those are short? So that's going to be Bayes' theorem. So this right here was law of total probability. This is going to be Bayes' theorem, which is going to be probability of Word given short times probability of short over probability of Word. And normally I would stick this whole thing in the denominator, but I already have it. So it's going to be over 0.66. And now probability of Word given short is 0.8 times probability of short, which is 0.6. So 0.8 times 0.6 over 0.66, I get, as I rounded, I think, 0.7273. So that's the probability that it is a short document given that it's a Word document. So basically 73% of the Word documents are short. Compared with what were we given? We were given 80% of the short reviews were written in Word. So this is saying 73% of the Word documents are short. So compared to 80% of the short documents being in Word. So you see how that percentage is like a different thing. You're calculating something totally different. All right, so let's look at number 2. What's the probability that it's medium given that it's a Word document? Well, that should be probability of Word given medium times probability of medium over probability of Word. Again, I already calculated the denominator in part A, so we don't have to redo that. Now, probability of Word given medium is 0.5. Probability of medium is 0.3. Multiply those. You get, I think I rounded again, 0.2273. And then the last one, it says find the probability of long given that it's a Word document. Well, it actually should just be 1 minus these two, of course. But we'll go ahead and calculate just to make sure that we get the right number. It should be probability of Word given long times probability of long over probability of Word, which is 0.3 times 0.1 over 0.66. And that turns out to be 0.0454, I think, which is actually 1 minus these two, because of all your Word documents, it has to be one of these 3. So that kind of is like a sanity check, I guess you could say. But yeah, that's the example I wanted to go over with Bayes' theorem. It's a little more tricky. It's a good one. I think Bayes' theorem just takes a lot of practice. You got to get used to, what's the information that you're actually given? What are you being asked? How do you translate it? How do you incorporate that denominator? How do you calculate that? So it's just a lot of things to keep track of with Bayes' theorem. So that's pretty much it for chapter 2. That's just the introductory, probability basics chapter. So let's see. It says, can you explain the difference in the rotation or the notation L given W versus W given L again. Okay, yeah. Let's look at it directly in this example. Like W given M. Given that it's a medium length document, then 50% of those are Word documents. Whereas given that it's a Word document, what's the probability that it's medium in length? Well, that's only 22.73%. So 22.73% of the Word documents are medium length, compared to 50% of the medium length documents are Word documents. So it's like, given that it's a medium length document, what's the probability that it's a Word document? Well, 50%. 50% of the medium length documents are Word documents, compared to, of the Word documents, how many of them are medium in length? That's 0.2273 or 22.73%. So it's a totally different, it's a totally different question altogether, or a totally different idea or thing that you're trying to answer. Not sure if that helps. Awesome. Good stuff. Yeah, it's definitely, conditional probability is probably the hardest thing from this chapter and Bayes Theorem. Independence is pretty straightforward, I think, once you get the right probability written out. If you can just use independence, that really helps. So yeah, that's good stuff. Not sure if there are any other questions. Just want to hang out here for a minute. I can go back and look at any other stuff that we've covered as well. Just let me know. Awesome. Looking good. Yeah, so like I said, go back over some of the examples and just kind of change up the scenarios a little bit. Yeah, I mean, even you could say LaTeX in this one too. So you said if you found the % short Word documents in number 2 and the % medium Word documents in number 2, can you subtract them from 100% to find the remaining? Or is it better not to, since it's a different question? I'm trying to see what you mean. I'll get to Rachel in a second. Yeah, so these recordings, these videos are automatically going to be uploaded to my YouTube channel. I'm going to keep these live streams as videos, so you can keep viewing them. It's not going to be the same problem that we're having with Zoom, trying to get them to process it for us. YouTube's going to process it and let me know when it's ready, and then yeah, you'll be able to rewatch this as much as you possibly want. So, all right, so let me look at this question. If you found the % short Word docs in number 2 and the % medium Word docs in number 2, can you subtract them from 100% to find the remaining, or is it better not to, since they are different questions? Do you mean, I'm going to see if I can, do you mean if I find these two, then this one equals 1 minus 0.7273 minus 0.2273? Yes, if that's what you mean. Like those two should add together to give you 1 minus the last one. Because it's exhaustive, the only types of Word documents we have are short, medium, and long. So it's complementary. Long's complement is medium or short. Medium's complement would be short or long. Short's complement would be medium or long. Yes. Okay, cool. I know I've got a little delay here in the comment section, so yeah. Good question. It's really good. Sometimes you can use that complement thing, kind of like here. These are complements. So these are complements. Because if it's a short document, it's either Word or LaTeX. If Word is 0.8, then LaTeX has to be 0.2. Same thing here. If it's a medium document, then 50% of them are Word, then the other 50% have to be LaTeX. And the same thing here. If it's a long document and 30% are Word, then the other 70% have to be LaTeX. That's correct. These are all disjoint. So short is disjoint from medium, and that's also disjoint from long because of the page restriction, right? The short was 1 to 2 pages. That's distinct from medium, which is 3 to 4 pages, which is distinct from long, which is 5 to 6 pages. That's exactly right. Precisely. That's right. So Bayes theorem, super important. Definitely going to be like a question or two using law of total probability and Bayes theorem on the exam. You're going to want to look out for stuff like that. So also conditional probability, independence, knowing when to use independence, what is the product formula or whatever, the multiplication principle. You can't always use independence, so be careful, only when it says they're independent. So these are things you want to keep in mind while you're working problems. And I just, like I said, I told you, I just stole problems from the book. Like this is one of the book problems. Like this is a perfectly good, test question. So book problems are awesome. So what if short was 1 to 2, medium was 2 to 3, and long was 3 to 4? We'd have to have more information. I think we would have to know what portion are 2 pages. So like what percentage is 2 pages, and then we would have the intersection of short and medium. And the same thing for medium and long. We would have to know what percentage are exactly 3 pages, or are 3 pages. And then we would have the intersection of medium and long, and then we could work the problem because we'd have those intersections. So if we needed to take anything like that, that would make it a lot more complicated. So I don't think you're gonna have to worry about that too much. But if it comes up, we'll think through it. But we would definitely need those intersections, or some way to get those intersections at least. So yeah, somehow that would need to be provided. Good question. Yeah, that would make it difficult, but possibly still doable. Good question. Sweet, not bad. I know 30 minutes is a little short, but yeah, we just might call it a day. Trying to still get our feet under us with all the changes going on. So let's just call it a day, I guess, for now. You go keep working on your homework or whatever, and send me questions or whatever's going on, and I'll try to help you out. So if there aren't any other questions, we'll just end it for now, and I'll see you guys next time.